We're now ready to begin our next major topic, program optimization. In this video, we're just going to give an overview discussing why we want to perform optimization and what the trade-offs are for compilers in deciding what kinds of optimizations to implement. Optimization is the last compiler phase that we're going to discuss. Let's just very briefly review the compiler phases. First, there's lexical analysis, and then that's followed by parsing. And then we have semantic analysis. And after that, we talked about code generation. And now we're going to talk about optimization. Okay, so optimization actually comes before code generation because we want to improve the program before we commit it to machine code. But it is, of course, the last one that we've discussed. But just to point out here, optimization fits in between generally semantic analysis and code generation. And in modern compilers, this is where most of the action is. It usually has by far the most code, and it's also the most complex part of the compiler. Now, a very basic question is when we should perform optimizations, and we actually have some choices. We could perform them on the abstract syntax tree, and a big advantage of that is that it's machine independent. But for many optimizations we want to do, it turns out that the abstract syntax tree will be too high level, that we can't actually even express the optimizations we want to perform because those optimizations depend on lower level details of the machine or of the kind of machine that we're generating code for that aren't present in the abstract syntax tree. Another possibility would be to perform optimizations directly on assembly language. And the advantage here is that all the details of the machine are exposed. We can see everything that the machine is doing. We can talk about all of the resources of the machine. And so in principle, any optimization we want to perform can be expressed at the assembly language level. Now, a disadvantage of doing optimizations on assembly language is that they are machine dependent, and then we would have to potentially re-implement our optimizations for each new kind of architecture. And so, as we mentioned in the previous video, another option is to use an intermediate language. And the intermediate language has the advantage, potentially, if it's designed well, of still being machine independent, meaning it can be a little bit above the level of the concrete details of very, very specific architectures, and it can still represent a large family of machines, but while at the same time exposing enough optimization opportunities that the compiler can do a good job of improving the program's performance. So we will be looking at optimizations that work on an intermediate language that has operations given by this grammar. So in this case, a program is a sequence of statements, and a statement consists of either an assignment, which could be a simple copy, or a unary or binary operation. We can push and pop things from a stack, and then we have a couple of different kinds of jumps. We have a comparison and jump, where we compare the values of two registers and then conditionally jump to a label. We have unconditional jumps, and finally there are labels, the targets of jumps. And the identifiers here are the register names, and we could also use immediate values on the right-hand side of operations instead of registers. And the typical operators, we're just going to assume some typical family of operators like plus, minus, times, etc. Now, optimizations typically work on groups of statements. And one of the most important and useful statement groupings is the basic block. So a basic block is a sequence of instructions, and typically we want it to be the longest possible sequence of instructions, so we want it to be maximal. And this sequence has two properties. First of all, there are no labels, except possibly for the very first instruction, and there are no jumps anywhere in this sequence of instructions except possibly for the last instruction. And a basic block, the idea behind a basic block, and the reason we require these two properties, is that it's guaranteed to flow, execution is guaranteed to proceed from the first statement in the block to the last statement in the block. So the flow of control within a basic block is completely predictable. Once we enter the block, once we begin at the first statement of the block, which might have a label, there will be a sequence of statements that must all execute before we reach the last statement, which could potentially be a jump to some other part of the code. But once we get here, once we get to this very first statement, that we're guaranteed to execute the entire block without jumping out. And furthermore, there's no way to jump into the block. You couldn't just come from some other random part of the program and begin execution, say, at the second or third instruction. The only way into the block is through the first statement, and the only way out is through the last statement. So here's an example basic block. And just to show you why basic blocks are useful, let's observe that we can actually optimize this piece of code. Okay, because 3 always executes after 2, this instruction here always executes after this instruction, we could change that third instruction to be w equals 3 times x. Okay, because we can see here that t is getting x plus x, or 2 times x, and here we're adding in another x, and so w is actually always equal to 3 times x. And a question then, so that is certainly a correct optimization, and it's correct exactly because statement 2 is always guaranteed to execute before statement 3. Another question might be is whether we could eliminate this statement. So once we replace this by 3 times x, maybe we don't need this assignment anymore. If this was the only place that t was used, if t was a temporary value that was computed only to compute the value w, and then we can delete this statement. And this depends on the rest of the program. We have to know whether t has any other uses someplace else in the program, which we can't see just by looking at the single basic block. The next important grouping of statements is a control flow graph. And a control flow graph is just a graph of basic blocks. And so there is an edge from block A to block B if execution can pass from the last instruction in A to the first instruction of B. So essentially the control flow graph just shows how control flow can pass between the blocks. And there is, of course, no interesting control flow within a block. We know that the basic block will just execute from the first instruction to the last instruction. So the control flow graph is a way of summarizing the interesting decision points in a procedure or other piece of code, showing where some interesting control flow decision is actually made. So here's a simple control flow graph. It consists of 2 basic blocks. The first basic block is outside of a loop and consists of some initialization code. And then we have 1 basic block here in the loop. The basic block consists of these 3 instructions. And at the bottom of the block is a branch, or a testing branch, where either we exit and go someplace else, or we loop around and execute the loop body again. Okay? And the body of a method can always be represented as a control flow graph. The convention that we'll use is always a distinguished entry node, so there's a distinguished start node of the control flow graph, and typically it'll just be obvious, it'll be the one listed at the top. And then there'll be some return nodes, or some nodes which you can return from, and you have a return statement in the procedure. And return nodes, or places where you exit the procedure, will always be terminal, meaning there will be no edges out of those blocks. Now, the purpose of optimization is to improve a program's resource utilization. And for the purposes of this class, when we talk about optimization in our examples and in the videos, we're going to be talking about execution time. We're going to be talking about making the program run faster. And this is mostly what people are interested in. So most compilers do spend quite a bit of effort on making programs run faster. But it's important to realize that there are many other resources that we could optimize for, and actually for any resource that you can imagine, there probably is a compiler out there that spends some effort optimizing for it in certain domains of application. So for example, there are compilers, we might care about code size, we might care about the number of network messages sent. Other things that are commonly optimized for are memory usage, disk accesses, so databases, for example, try to minimize the number of times you access the disk, and power for battery-powered devices. And the important thing about optimization is that it should not alter what the program computes. The answer still must be the same. Okay, so we're allowed to improve the program's resource utilization, but we can't change what the program will produce. Now, for languages like C and Cool, and all the languages that you're probably familiar with, there are three granularities of optimization that people typically talk about. One is called local optimization, and those are optimizations that apply to a basic block in isolation. So these are optimizations that occur within a single basic block. Then there are what are called global optimizations, and this is really misnamed because it's not global across the entire program. What people mean by global optimization is that it implies to a control flow graph. It's global across an entire function. Right? So global optimizations would apply to a single function and optimize across all the basic blocks of that function. And finally, there are interprocedural optimizations. These are optimizations that work across method boundaries. They take multiple functions and move things around to try to optimize the collection of functions as a whole. Now, many compilers do one. In fact, almost all compilers do one. Many compilers today do two, but not very many actually do three. Okay, so you see decreasing numbers of compilers doing these optimizations as you move up in the granularity. And partly that's because the optimizations are more difficult to implement, so it's just more work to implement the interprocedural optimizations, but also because a lot of the payoff is in the more local optimizations. So expanding on that last point a little bit more, it turns out that in practice, while we know how to do many optimizations, often a conscious decision is made not to implement the fanciest optimization that is known in the research literature. And that's kind of an unfortunate thing from my point of view, being somebody who's really likes compilers and spent a lot of time thinking about optimization. And maybe it's a little bit hard to accept for the professional compiler researchers that people don't always want to implement the latest and greatest optimizations. But it's worth understanding why that might not be the case. And it boils down essentially to software engineering. Some of these optimizations are really hard to implement. I mean, they're just complicated to implement. Some of the optimizations are costly in compilation time. So even though the compiling happens offline and is not part of the running of the program, the programmer still has to wait while the optimizing compiler does its compilation. And if it takes hours or in some cases days to optimize a program, that's not necessarily great. And some of these optimizations have low payoff. They might always improve the program, but they might only do it by a very small amount. And unfortunately, many of the fanciest optimizations in the literature have all three of these properties. They're complicated, they take a long time to run, and they don't do very much. And so it's not so surprising that not all of these get implemented in production compilers. And this actually points out what the real goal is in optimization. What we really want is maximum benefit for minimum cost. We're really talking about a cost-benefit ratio. So like optimization costs a certain amount in code complexity of the compiler, in programmer time, waiting for the compiler to run. And the benefit, the amount that it improves the program, has to be sufficient to justify those costs.